So last time we talked about how to evaluate limits using a graph. So I gave you the picture and then you evaluated the limit. Here I'm giving you some characteristics of a function, and then you have to try to sketch a function that would have these characteristics. So a lot of people don't like this because there's not just one set way. Everybody's answer should look a little bit different. And most people like to say, show me how to do it so I can just do it the way you did it. No, these are a little bit different, but I can give you some hints, all right? So in this case, I have a point and I have a limit. So I always start with the limit. So if the limit exists, let's flip back over to the other side. Remember, we said that the limit exists in any of these three scenarios. So my graph either is continuous, it meets at a point, or my graph has a hole, it meets, but it doesn't actually get to a point. There's not a point there. And then here, my graph, both sides meet, but the point is somewhere else. So in either scenario, my graph the two branches of the graph have to come together. Now, whether they come together at a point, or they come together at a hole, or they come together at a hole with a point somewhere else, depends. But if the limit exists, I know it has to be one of those three scenarios. So if my limit exists at 3, what I'm going to do is I'm going to start off my graph with a hole, because I can always fill in the hole later. I don't want to start off with a point, because sometimes the graph doesn't actually meet at a point. Now, in this case, it will, but you'll see later on that it doesn't always do that. So as x approaches 1, my graph needs to approach 3. So as x approaches 1, my graph needs to approach 3. That means I'm going to draw a little bit of the graph. So I'm going to draw a little bit of the picture. So we have to meet here. So this side, the left side has to meet at 3, approach 3, and the right side has to approach 3. Now, after I figured out this, then I can look back at my point. My point is at 1, 3, 1, 3. So now I can go back and I can fill in that hole. And then I still have to draw an actual curve here. I have to draw my picture. So I can do whatever I want as long as I don't violate the vertical line test. I can make my picture look something like that. So graphically, what is this? This is graphically my limit exists and my point exists, and they exist at the same place. This is what we call a continuous function. Our graph is continuous when those two things occur. Okay, so our function is continuous. That means that the two branches have to meet at the same place, and the point has to be at the same place at x equals -1, but a cusp appears. So this is more for my AP Calc kids. I just want to talk about what this word cusp means and what that looks like. So my graph just has to meet at -1, but it has to create a cusp. A cusp looks something like, it didn't say where we had to meet, so I'm going to say, okay, I'm going to meet here. This is what we call a cusp. It's also known as a sharp turn. Ugh, I really don't like the way I drew that. Let me draw one up here. So it would go up, something like that. That's a better cusp. So my graph comes in, it meets, and it creates this thing called a cusp. This is still continuous, though. I mean, they told us that right off the bat. You might also hear this called a sharp turn. And like I said, those of you who will ever take calculus, we use this terminology quite a bit. All right, so moving on. Next up, don't start with the point. I really recommend starting with the limit, because that's what the whole graph is doing. And then you can go back and decide if you have a point or not. So in this case, it says the limit exists. That means that my graph has to meet at -2, my graph has to meet at a height of 2. It intends to meet at a height of 2. So at -2, I'm going to go up to 2. I'm going to leave an open circle for now, because I can always fill it in later. I can't well, if you have a pencil, you can. But I need my graph to meet. So I'm going to draw just a little bit of the graph, a little bit on this side and a little bit on this side. Okay, now from there, I can decide whether or not I need to have a point. It says f of 2 is undefined. So as I go up and down at -2, there are no points. So now I can just draw whatever I want for my curve from here. Something like that. And then graphically, what do we call this situation? This is what we call a hole. So the limit exists, the graph actually meets there, but there's no point. So you went to McDonald's, I went to McDonald's, but there ain't no McDonald's. Okay, so my limit exists. Start with the limit. My limit exists. That means from the left and from the right, my graph, as I approach -1 on the x-axis, my height has to approach -2. So -1 needs to approach -2. I'm going to start with an open circle. And I'm going to draw a little bit. So I'm going to make the graph approach from both sides. My actual point, though, is at -1, +3. So my point is somewhere up here floating in space. That's legal. So I don't really have anything else to draw here, so I can just draw my graph however. And what do we call this? See if you can remember from the front. So this is what I call a holy jump. It comes in, it jumps out real quick, but then jumps right back in and comes out the other side to create a hole. So in my class, we're going to call this a holy jump. All right, finally we're going to get into some situations where the limit does not exist. So if we flip over again, the limit does not exist in two scenarios, a jump or an asymptote. So usually if you have some point defined, asymptotes are usually the easiest to tell because their limit does not exist and nor is there a point there. So that's usually the easiest one to draw or to recognize. This, a jump, is when you do have a point, but you don't have the branches of the graph meeting. So in this case, I am actually going to start with the point because I just need to make sure that my graph doesn't meet. So I know it's not going to meet, so I can't draw the hole because I don't know where the hole is going to be. But at 0, 2, my graph hits that height. Now, I need the graph to not meet. That means from the left and from the right, they need to not be at the same spot. So let's say from the left, I go in. Notice I'm just drawing a little bit of my curve. Now, I can't draw going out the other side, otherwise my two branches would meet. So I need to jump somewhere else. Well, where do you jump? Anywhere along that same x value. So I can pick any spot. I'm going to jump here. Now, as I jump here, should this be a hole or a point? It's got to be a hole. If it were a point, our function would violate the vertical line test. Okay, so now look at what happened. Your graph came in here. It jumped. Well, it can't jump and go back out the way it already came, so it comes out this other side. Now I can go back and I can make a sketch. This is what I decided my graph was going to look like. So my graph comes in to a height of 2 from the left and comes into a height of -1 from the right, which means they don't touch. We call this a jump. All right, the next one, this is the easiest one to draw. You've got a limit that does not exist, and you've got so your branches don't meet, and you don't have a point there. So it's going to be, the easiest way to draw this is with an asymptote. You can actually draw it another way, and I'll show you in a second, but I usually draw this with an asymptote. So my graph needs to not meet nor have a point. So I'm going to indicate that at x equals 1 with an asymptote. Now, it doesn't say which way our graph goes from either side, so it doesn't matter. You can pick. You can draw whatever you want. You just have to make sure you draw something on either side. There we go. There we go. Notice I didn't violate the vertical line test. Notice I went asymptotic. I went towards the asymptotes. The asymptotes block the sides. Now, you could have made them both point downward. I don't care. That's fine, too. This is what we call an asymptote. So I said there was another way that you could draw a limit that does not exist and a point that does not exist without drawing an asymptote. So the other way to have a limit not exist is to go to a jump, right? Now the difference here compared to what we just did, in this case, we jumped and one of the points were actually defined. In this case, neither of the points are defined. So does my graph meet? Nope. Does my graph have a point? Nope. So this is the other option. We would still just call this a jump. We don't call it like a holy jump or anything. It's just called a jump. That's the other. Both of these are acceptable ways to represent these characteristics. Okay, so now we're getting a little more specific here. I'm still going to start with my limits, but this time it's telling me what to do. It's not really giving me a choice here. So it's saying as you come in from the left. As x approaches 1 from the left, you should approach -1. So I'm going to go to 1. From the left, we should be approaching -1. Notice I made that an open circle because I can fill it in later if I need to. And this is coming from the left. So the graph comes in and meets there. As x approaches 1 from the right, our graph needs to reach a height of 2. So up here at 2, we're going to approach from the right. And notice I just did a little bit. I can draw the rest later. And then f of 1 equals 2. That means at 1, my graph needs to reach a height of 2. So I actually filled in that one, this one. Going to go that way. That one's going to go down as well. There's my graph. All right, what do we call this? Where the two branches come together but they don't meet, we call that a jump. And then the last scenario, well, I'm going to pause it and see if you can try this on your own. Okay, so as you come from the left, our graph is going to go up, 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 up. As we come to -2 from the right, our graph's going to go down, 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 down. And there's also no point there. So what? This has got to be a what? Hopefully you said asymptote, and that's exactly what you must. There's no real option here. So as I come from the left, my graph needs to be headed towards positive infinity. Oh boy, I didn't leave much room here. There we go. As I come in, this side's going up towards positive infinity. As I approach from the right, I need to head towards negative infinity. So this time I'm going to go like this, make it something fun. Now I don't care that this side goes up. All I care about, all I know is what's happening near this asymptote. And graphically, we call this an asymptote. All right, give that homework a try. Good luck.